We have a fairly ambitious agenda. So first of all, go through meta-analysis in R, the third section of it, and that includes questions like inference analysis, cumulative analysis, as well as heterogeneity. Then we will introduce prevalence meta-analysis. I know that a lot of groups are doing projects that are related to prevalence, but for the purpose of prevalence, what we will do is that we'll first of all introduce it in R, and then we will quickly look at how it is done in SPSS. It's not very complicated. If you've followed the analysis from the previous sessions, how we have done different other types of meta-analysis, you would realize that this is just an extension to it, right? So once we do that, the next thing that we will do will then be to come back and talk about indirect treatment analysis. So it's going to depend on how much time we have. And if we're not able to get to indirect treatment meta-analysis, then the code is here for anyone who is interested. Basically, indirect treatment meta-analysis is useful when you have two or more interventions. So for much of the time that we've been talking about in this class, we have looked at scenarios where you have compared maybe a treatment and a control group, or so media campaigns versus no media campaigns, or maybe an hypertension drug versus placebo. But there's some scenarios where you want to compare multiple hypertension drugs against each other, right? And you're looking at data where each one of them is compared against one other one or against more than one, but you're really looking at data where, you're not going to be able to see all the different comparators in the same paper. So you want to pull that together. That's where we use indirect treatment meta-analysis. So if we get to that point, I'll describe in more detail. So let's get started. In the previous class, we've been looking at one example, the extent to which media campaigns increase the proportion of participants in the sample who consume up to 5 servings of fruits and vegetables per day. And that's the ratio setting, that's the dichotomous outcome setting. But we've also looked at examples where media campaigns increases the mean intake of servings of fruits per day, and that's the continuous outcome setting. So if we look at the dichotomous outcome setting, that's what we're going to use as an example today, but everything that we're going to teach for inference analysis, cumulative meta-analysis, heterogeneity, they have the same basic sets of code, so we won't go through it more than once. So first of all, this is R. I imagine that you've opened the R file on your computer, so I will run this code to clear this space. If at any point in time you think I should slow down, please speak up and let me know. Or if you want me to go over any concept again, please let me know. So this clears the workspace and allows us to, start afresh, so to speak. And then the next thing that we will do, I don't know if anyone has pointed it out to you, but you see on this right side, there is the outline. The outline allows us, it's kind of like a contents page. It allows us to jump from different parts of the code to another. So if you have a code that runs and runs, like in this case, this is 400 lines in this file, right? And if you're trying to move back and forth, it's going to be easier to just click the outline. So the way to create the outline is to use this hash. So the hash, one hash, and then 2 hashes or 3 will allow you to subset, right? So this working setting, if I wanted to go to prevalence meta-analysis, I'll just click here and that takes me all the way to 254. If I want to go all the way to the end, this is the last chunk of code, publication bias. So, all right, so let's get back to the beginning. So in influence analysis, and we talked about this when we were looking at RevMan last week. So if you were in that class, it's basically a repetition. So in influence analysis, what we're really looking at is to understand the extent to which one single paper might be influencing, that's the word, influencing the overall pooled estimate. So if you do a meta-analysis and the pooled estimate from maybe 10 papers is 0.40. Let's assume it's a relative risk. But for each of those 12 papers, right, there are studies that have estimates like 0.9. There are studies that have estimates like 0.1. And there are studies that are all over the place in terms of where their own relative risk estimate lies, right? So the influence analysis essentially looks at all the studies and tells us which one of them is really pulling the data in one direction or the other, right? So if you think about a tug of war, right, you have so many people on one side, so many people on the other side. So if you release your arm, those other guys fall to the other side. That's essentially what this is doing. Okay, so the way that we do influence analysis is what is called leave one out meta-analysis. So basically, you have 12 studies, you do the meta-analysis, you note what the pooled estimate is, say 0.4, and then you drop one study. Say you drop the first study, and you rerun the meta-analysis with the 11 studies that are left, right? So now the pooled estimate that you have might be 0.5. You had 0.4 before, and then you return that study back in, you take out the second study, you rerun the meta-analysis, and now you have maybe a pooled estimate of 0.42, right? So you then do that until you get to the end, and then you look at all your estimates and say, looking at these estimates, which one of them, which study is it that when we take it out, meaningfully changes the results that we find? That's essentially the concept of influence analysis, leave one out. Okay. And you might ask, how much change is important? And the truth is that there are no rules per se. Most times people look at the estimates and say, if it changes more than 10% or 20%, then I would pay attention. Or if the direction of the p-value is changing, then you might want to pay attention. Those are the kind of things that you look at. Maybe if the I squared is changing, then maybe you might want to pay attention. And so when you find that one study is drawing the estimate significant like that, you go back and you look at that study and try to understand why that is the case. Sometimes it might mean that there's an error in the numbers that you have input, or sometimes it might mean that that one study is different in some way. Maybe some characteristic of the study makes it different. But the purpose of influence analysis is to figure out outliers in your analysis that you can look at and try to understand why they're outlying. And if there are changes that you need to be making to your analysis, you make them. If there are no changes, there's some description that you need to do in your result to explain what you're seeing, then you do that as well. Okay. So in this analysis that we just did, in this media campaigns and 5 servings of fruits per day analysis, first of all, you load the data, and that this is the code to load the data. These are the library for importing Excel file into R. This is dplyr, which helps us to manage the data. And in this class, we have looked at 2 packages for meta-analysis. There are others, but we focus on metaphor and meta. So in this one now we're looking at, this is library metaphor, where if you run this chunk of code, this chunk of code basically is the same basic meta-analysis code that we have seen again and again in this class. And this summary statement will give us the results of the meta-analysis. So this is the code that runs the meta-analysis and then stores it in this object FE model 1. And this summary statement will output the object and let us understand what it is that we're looking at. So I'll run this now. And so can someone quickly tell us what we are looking at? What kind of meta-analysis is this? How many studies are there? What's the I squared? What does the I squared mean? Where is the pooled estimate? What does the p-value mean? That kind of thing. Anyone? The reason we keep going back and forth as far as the interpretation is concerned is because we think that that's the most important thing to take away from the class, whether you learn how to do the analysis or not. So the most important thing is that when you see the results in publications, you can engage with them, right? That's the minimum takeaway that we expect from this class. Anyone? I know that this is probably very simple now, but please go ahead, Chiluka.
Okay, thank you. This is a fixed effect model meta-analysis for 13 studies. And the test for heterogeneity shows that the study is 85.34%, which is considerate. And the effect estimate is 0.300. And the confidence interval lies between 0.2801 to 0.3799.
How do you interpret that?
So since basically what we are looking at, the effect of a media campaign on fruit and vegetable consumption, then it implies that for each unit increase in media campaign, there is a 0.330 increase in consumption in fruits and vegetable consumption.
Okay, all right. So yeah, thank you. So the thing is that it might be a little challenging to explain this estimate because what we're looking at is the log transformed version of the result. So we have to exponentiate. So that's one of the things that the forest plot will do for us. So if we run the forest plot, let me do that. This forest statement will already have factored in the exponentiation. So FE model 1, I think that's what it's called. Right? Yep. Okay. So if you run this now, you'll see that okay, let me see, I think that. Right, so okay, that doesn't look right to me. Yeah, this is log risk ratio, so it does look right. So this is the log risk ratio. You see that this is the log risk ratio. So ideally, we should have included in the code statement something that tells how to exponentiate. So you're right that for every 1 unit increase, that means that if you go from not having media campaigns to having media campaigns, there is an increase. Yes, there's an increase in the likelihood of intake of fruits and vegetables up to 5 servings per day. So yeah, so you are correct. All right, so that's the interpretation of that analysis. And so that now when we come to influence analysis, which I just explained as essentially.
Excuse me.
Yes,
please,
go ahead.
Sorry, I don't know. Will it be possible for you to also explain to us how to, like now, I want to write a code in R, how you developed your R markdown pages then, so that you can use it to run your codes. And also, I've been finding it a little bit difficult to knit too. If you can show us how to knit. Sometimes, at a point I wanted to knit some of your outputs, and was showing that there were errors in the arguments.
Okay.
I tried to. Okay, thank you.
Okay, yeah, that's helpful. Yeah, I think that you had also mentioned this in the Google Classroom at some point, and thank you very much for raising it. So I'm trying to knit, and let's see if it does knit, and then I'll just walk you through. Sometimes it doesn't knit if there's an error in the code, and there's sometimes errors because you write a code that should help you show something. Okay, it does knit. 1 second. Let me show you what the output looks like. Should go to downloads. Oh no, right here. All right. So this is what it looks like when you knit. Okay. But I'll go back and just walk you through how we get here. I think that's an important question that we should have addressed at the beginning. Okay. So if you have, when you open your R, right, the first thing that you do is go to File, New File, right? And when you open New File, there's a number of different kinds of R files that you will see,
Good
right?
afternoon.
Yes, hi.
Okay.
I think that person is on the phone. So there's a number of different kinds of R files that you will see when you open New File. And there's R scripts, there is R markdown. I'm just going to go through very quickly what it would look like if you have R markdown and R script. So if you have R script, it will open as a blank page that looks like this. Okay, and you will write your code. So say if I were to write this code to import, let's say this library, just that. Yeah. So you will need to select it and to run it, right? That's how this works. And if you see that this doesn't, it's just plain coding interface. And this is the same thing that you would have if you have used Stata before. This is what that interface looks like. But what R Markdown does is that it makes it easier for you to like separate parts of your code, right? So here you can write a title, author, blah, 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 but I'll just skip all that. And when you open your R Markdown, this is what it looks like, a new R Markdown, right? And it has some explanation. So R Markdown is supposed to make writing code in R easier for you, supposed to make it more user-friendly. So there are explanations about what an R Markdown is, and this is an example of a code chunk, and again, multiple examples, but this CARS is a data set that comes with R. So if you run this, you will see something. It will give you the summary, right? And you can plot if you run this, okay? But this is not something so since we're not interested in that, we'll typically just delete all of this, right? And, and start afresh. So then this is just neat that comes also with the R code. So here, if you're going to write a new code chunk, we'll typically hold down Control Alt I, and then you can write in this code. So if you remember that library read Excel that I ran earlier, you can run it here again. And you can look at the results, the findings in the console below. Just telling you that it has run the library. And if it's the same summary CARS statement, you will see how R Markdown is different from, okay, we already did that. So yeah. So this is basically how you set it up, right? So, but if you already receive code, you can just edit the same code. So, so this is code that we already prepared, and you can edit it, try out different things. So typically, many of us learn R by, first of all, engaging with the code that others have. Good thing we have annotated this code as much as possible to just explain what is going on in the code. A lot of people might not. So many people write code and they don't annotate it like this. So when you start writing your own code, you should, or when you write your own code, you should make it a habit to annotate and to add outlines that make it easy for you to go back and forth. So yeah, so if you are going to knit, right? If you're going to knit, if you have this code statement at the beginning of your code, like in this case, right? Then all you need to do is to click this knit here. Now, if this knit icon is not appearing in your R code, it might mean that some package is missing from your code, right? I think there's library knit R or something like that that you need to install. But if you don't, if it's not running, then if it's not present in your, just when you open it, it should be there. If that's not the case, then you need to check your maybe somehow something during the installation or maybe the settings. But if you have it showing like this, then you just need to click this downward arrow and choose where you want to knit it to. I typically knit to Word because then I can edit it however I like. So if you knit to Word, you will see that in your console here in this interface, it's showing exactly what's going on. And once it's done, you will find it in this folder. This, for me, it's course material / meta-analysis 101. So, and that is this is where it should be, course material / here, right? So that's this file. And if you right click, I can open that file. Okay. And if you wanted to knit to something else, sometimes there's some reason the knit might not work. It might not work because there's an error in your code. If there's an error in all of your code, then knit will not work. Or it might not work because there's something wrong with your package. So I think you should take a look. But when you knit, it should include all of the code, right? As well as all of the results. All of the code, all of the results, as well as the annotations, all this text that we have in between, explaining what we're doing, it should include it. So sometimes when you want to submit an assignment, for instance, you will just knit and then send this to whoever it is that you want. And then sometimes as well, there is the option to use LaTeX. That's something else differently, where you can essentially write all your code and it will output the way that your paper is going to look. So that's another option for something that to think about. So that's by the side. I hope that helps, Chiloka.
Yes.
Okay.
Thank you.
Okay, yeah, you're welcome. So let's keep going. So inference analysis. So we've explained what inference analysis is. Now, when you run this code, you'll get an output that looks like this, right? But before you can interpret it, you have to go back and look at your meta-analysis. This was 0.33, right? That's your pooled estimate. And your I-squared was 85, and the p-value was less than 0.001. So you note those. So when you look at the inference analysis output, you compare the estimates in that pooled analysis to this one, right? We had 0.33 there, this is 0.31. So you have to ask yourself, do I want to use 10%, 20%? What do I want to do? So say I'm going to use 20%. So if I want to use 20% or 0.33, that means that any estimate that's ballpark that goes outside of 0.26 or outside of 0.4, for instance, then I will pay attention to those. So now if you look at all of these estimates, you notice that this second one, right? This second one is 0.42, which is above 0.40. And if you look, so that's 1, 2, 3, 4, 10, up to 10. And there's more papers here. None of them goes below 0.26, but we have one that goes above 0.40. So you might think maybe it means that once we take out this study two, right, then the estimates are changing a lot. So maybe study two is exerting a lot of influence on the pooled estimate, right? So that's one. You could also look at, you might also look at the p-value, the p-value is consistent, less than 0.001. This is hard to interpret because, less than 0.001 means so many things. It might be 10 zeros or it might be 20 zeros. We don't know. But if you look at I squared, you might want to look at the I squared. So the I squared above is 85%, right? So here for that second study is going below 80%, right? And this one as well is going to be below 80%. And but that's it. We don't have any studies going above 90. So you just generate some ballpark in your head of what do you think is a meaningfully different set of estimates, right? And if you think that this is meaningfully different, then you would look at the study that is leading to that difference, and then you go and try to understand that study. So in this case, the study in question is, let's see, let's look at that study quickly. So in this case, the study in question is this one, Abioye 2018. And so you would look at the study characteristics. It was in 2018, which is, most of the studies are in that same ballpark. What else? It was a US study. The coverage for this study was 22, which is a little low, right? But still, you have some other studies with coverage in that same region. And then you look at other characteristics. I don't think we have more information on other characteristics, but you look at other characteristics, right? So radio, there might be other things that you have not captured. So if there's factors that you have captured, you look at them, but if there are other things that you haven't captured, you might need to go back into the paper and try to understand what you're looking at. But that is influence analysis. Any questions? All right, so if we have no questions, moving on to cumulative meta-analysis. So with cumulative meta-analysis, the idea is that the year of the study can be expected to affect the findings. So for instance, an example that I gave last week was an HIV, right? In HIV, antiretroviral therapy became available at different levels, to different extents, right? In the beginning, very few people could afford it. It was very expensive, was not widely available. The research was not great. So few people were getting any antiretroviral therapy at all. But as time went by, right, we started to have antiretroviral therapy being available in more places. And then at some point, everyone could get antiretroviral therapy, but only if they met certain stringent clinical criteria. Like maybe they had to have CD4 meeting certain stage, WHO reaching certain level, WHO stage being 3 or 4, something like that. So, but today we now have a situation where we have a test and treat strategy where most people are initiating antiretroviral therapy the moment they're diagnosed with HIV or as soon as possible, right? So that change over time often affects the results that you look at when you're doing HIV research, because antiretroviral therapy is such a key component of the effectiveness of most studies, most interventions in this HIV space. Another example is something like surgery, where procedures are changing, techniques are changing. And today we have a lot of minimally invasive surgery that's as safe. It wasn't always as safe, right? So there's a lot of uptake of minimally invasive surgery. And even now we have robotics, right? So if you're doing a global study and you're examining the evidence, you should also check whether the fact that the study is recent compared to the fact that the study is made 20, 30 years ago, right? How is that affecting the results, right? So that is the whole point of cumulative meta-analysis, okay? Typically, you will first of all order the data set. So this is a chunk of code that first of all, we order the data set by year, right? And then we run, so basically you're rerunning so you have the first, you've already run the meta-analysis. You reorder meta-analysis data set. So it's not the full data set that you're reordering. It's the meta-analysis object, FE model 1. And then you repeat the forest plot on that, on this this new object that you have sorted, right? So if you run that, you will see that in this case we have initial one we had study by year, and we had study by numbering, but now we have the study by year, right? And so this tells you that this is a sorted data set. Study 8 was the earliest, the study 3 was the latest. And you can see the way it's written. It's basically saying study 8 plus study 12. So you start from the oldest study, and then you add the next study to it, and rerun the meta-analysis. And then you add the next study to it, and rerun the meta-analysis. And then you add, so you keep adding until you get to the final one. And this final estimate should be the same as your final estimate in your main meta-analysis above, right? So if you check, you will see that what we have here is 0.33. What we have above is also 0.33, right? And what can you notice about the pattern of these squares and the horizontal line between them in the middle? Anyone? What can we notice about these boxes, the pattern of the boxes? Just tell us what you see. It doesn't have to be any complicated technical term that you want to use. There isn't actually. It's just visual inspection. Anyone want to try?
I think for all the studies, only one of the study passes the line of no effect. And
Okay.
the confidence interval ranges from minus 3.0 to 0.79. The other studies had the smaller confidence intervals. Yes, the confidence interval did not touch the line of no effect.
Yes.
So I think what I'm looking at is that the study that has larger confidence interval, it might applies that the sample size is smaller.
So you're right about
larger.
this study. If the sample size is small. So
It's
you're
smaller,
right about
yes.
the study. Yeah. So if the sample size is small, you will have a wide confidence interval. But this second one, where the second box and the horizontal line represents study 8 and study 12 together. Okay. It represents study 8 and study 12 together. So you would expect that the confidence interval will get narrower, because as you add the two studies, now you're going to have more people in the study. So if you had 50 people in the first one and 50 people in the second one, now you will have 100 people represented here, right? And then the next one is you're adding the third study into the first two, like that, until you get to this estimate that's essentially a pooled estimate of everything. But you're right that it's only for this first iteration that we see that this is causing the null. For all others, it's not causing the null at all. Which tells us that very early in time, the effect of mass media campaigns on whether people are consuming adequate amounts of fruits and vegetables was significant very early. So it means that there isn't like such a strong influence of anyone. So there isn't like a strong influence of time, so to speak, where maybe we have after some time the studies are pulling this way. But what we're seeing here is that the studies are fairly consistent. This one is pulling to the right, but it soon stabilizes. That's the other thing that you should notice. At what point in a cumulative meta-analysis do the estimates become stable, where they're not going here and there and changing here and there? So here we're seeing that very fairly, by the time when we get into the fifth or sixth study, we're already seeing that stability. So that's what we have for this cumulative meta-analysis. There are some times when you will clearly see patterns where maybe the association was on the left side was not significant, and then it becomes significant, right? That's one pattern that you might see where you can clearly say that, okay, maybe at a certain, so it might be that maybe all the studies before year 2000 were negative studies, and then all the studies after year 2000 were positive studies. And you will ask yourself, what happened in year 2000 that, what happens in year 2000 that affects our result? Someone asks, what is the reason for the stabilization? And the reason why these estimates become stable is just that the sample size becomes large. So as the sample size becomes much larger, we will have estimates that become more stable. There isn't a lot of moving here and there, unless we then have something happen. Maybe around this time, something then happens, say COVID-19, for instance, happens, and then it completely flips the findings that we're looking at. So those are the things that you look at. What happened in time? Maybe in year 2000, the techniques of surgery changed, or maybe in the past, people were not using the internet, and then now they started to use the internet. That's the kind of thing that so you're going to need to contextualize your study by understanding, you're going to use the cumulative meta-analysis to sort of contextualize your study, right? So that's the thing. So the stabilization is mostly just averaging out, and you can think about this you can play around with numbers and see for yourself. If you're creating an average, right, and you start adding numbers, you will get to a point, say you start with 2, 5, 7, 8, you will get to a point where the average number that you will be getting will not be changing so much. And that's just what we're seeing here. It's that averaging out. So unless you then find a large outlier, it will not have an effect on the pooled estimate anymore. Okay. All right. So that's cumulative meta-analysis. The next one is heterogeneity. And with heterogeneity, what we're really trying to look at is also a way for us to contextualize our study, to try to understand why are we seeing what we're seeing, right? And with cumulative meta-analysis, we've tried to look at year to understand whether the year when the study was conducted affects the result. But with heterogeneity, we will look at other study characteristics. So it might be the location of the study, whether the study was conducted in Africa. It might be the coverage of the study, whether the coverage was large or small. It might be something about the way that the outcome was assessed. So in this case, we're looking at FFQs, whether you use food frequency questionnaires or you did not. If you didn't use food frequency questionnaires, you might have used other means to assess whether participants had intake up to 5 fruits and vegetables per day or not. So what you would then do, what this chunk of code does, is so we're using library table 1. So this library table 1 refers to this code where we're going to create a table. We'll get to that point in a moment. But this chunk of code we're basically just using to classify this variable as, and there's an error here. So we classify this variable as a character variable. In the original Excel document, this was a numeric variable. That's all this is doing. So we classify it as a character variable. So that allows us to create this table 1. It's table 1 that needs it to be a character variable. So if you run that code. Now, the reason why we're creating this table is just for us to look at the pattern, right? So in country, we have different countries that are where studies were conducted: Australia, Canada, Nigeria, Tanzania, United States. And then we have how many of them were African countries, right? And then we look at the coverage. This is the median coverage. This is a continuous variable. And this is coverage greater than 50, right? It's either yes or no. That's a dichotomous variable. So we will then, we're interested in understanding to what extent these characteristics might have influenced the pooled estimate that we're looking at, okay? And so we've talked about heterogeneity many times. We know that depending on the I-squared value that we get, it might be less than 40 is fair, 40 to 60 is moderate, 60 to 80 is substantial, more than 80 is considerable, and I-squared is a percentage, right? So the maximum possible is 100. And we said that if you find considerable estimate, then you should look again. You should look again and try to understand why your estimates are considerable. But you should definitely examine heterogeneity if your I-squared is moderate and above, maybe substantial and considerable, or sometimes you just decide that I'm going to examine heterogeneity regardless of the I-squared, and that's acceptable as well. Okay. So this is rerunning the code using the meta library, and yeah, so basically just running the code using the meta library, and this is what we get. In this case, we have exponentiated the estimate, so that 0.33 is the same thing as this 1.39 that we're looking at because this is exponentiated. Okay. So we will then. So the first thing I want to do is to examine the extent to which meta-regression differs by country, right? And we have 5 countries. So if you run this code, it will, here you're just looking whether country affects heterogeneity. So if you run this code and you look in the summary results that you get, okay, you will, this is a test of moderators that you're going to look at. And a quick explanation that this is basically taking the estimates that you have obtained in your model and then adding country to it as a regression, as if you're doing a regression, like a simple regression model, and then you read off the estimate. So this is the p-value of interest, 0.73. So this is the p-value of heterogeneity that tells us whether this moderator, the moderator in we're talking about here is country, has an impact on the result or not. This is really all that we're looking at, right? If it's significant, we might want to try to predict the estimate. So that's the second way that we assess heterogeneity. So the first way that we assess heterogeneity is just doing a meta-regression. This is a meta-regression, right? And then the second way that we assess heterogeneity is to try to predict estimates. Okay, and so if we have a prediction interval, if we have this model that we've just run, then we would use prediction intervals to try to understand for each country, what does this mean? But the key thing is that you will have to remember which country is 1, which country is 2, 3, 4, 5. And so if you run it, we will see that this prediction for 1, that means that in Australia, right, because Australia was the first one, if you go back to this table, 1, Australia was the first one, right? And Canada is the second. So here, this is the relative risk in Australia. It means that in Australia, if you did a media campaign, there was a 1.41-fold increased likelihood that people were going to be consuming more than 5 servings per day of fruits and vegetables. And the next one is for Canada, and the next one is for Nigeria, Tanzania, and the US, right? So this is really what you're doing with the prediction interval. And you can look at these estimates to see if there's anyone that's meaningfully different. They're all they're in the same ballpark. So that is why that's why this is not significant, But we might try other covariates. So for instance, this is Africa, and we're doing meta-regression and the prediction interval in the same code chunk. So if you run this is just basically for Africa. If you run this code chunk, we can see that the moderator here, the p-value here is significant, which tells us that there is something different between studies conducted in Africa versus studies that were conducted elsewhere. Okay, so now we're interested in the prediction interval. And so you might, if you then look at the prediction interval, it's this output. The one here is really 0 and 1. So 1 here is if this is not Africa, and 2 here is this is in Africa. So it means that if you did a media campaign in an African country, on average, you are going to be more effective than if you did a media campaign in a country that's not an African country. That's really what we're showing with this estimate. I'll stop here and take any questions that you might have. Or if I've completely lost you, please speak up and we can go back. Any questions here? So if we don't have any questions, I'll assume that this is perfectly clear. I mean, that makes sense considering we have looked at this in SPSS, we have looked at it in RevMan. So I'm hoping that you attended at least one of those classes, and that's where we're going quickly. But, if you have questions, please speak up. And we can repeat the same thing with FFQ. Did use an FFQ in this study or not, basically. So if you rerun this code, right? This is the test of moderators is the one that we're most interested in. And the p-value here is 0.95, which tells us that it doesn't matter, whether you use an FFQ or you do not use an FFQ to assess, right? So you can either look at the prediction interval and you will see that the estimates are fairly similar and the confidence intervals overlap. Okay, that's this one and that one. But I want to quickly show that what you will see when you're using a continuous variable like coverage, right? The coverage is a continuous variable in the sense that it can go from 0 to 100, or so it's kind of continuous. So if you have coverage as a variable, and we had studies where the coverage was 22, we had 23%, but we also had studies where the coverage was in the 90s, right? So if you run this code, this is the code that you use to assess. This is meta-regression code, and this summary will output the result, right? But for the prediction interval, you want to, because now you have 0, you have 20, 21, 30, you have many different potential numbers. But for prediction interval here, you will tell R that just give me an idea of what it would look like if coverage was 10%, or maybe if coverage was 50% or 90%, depending on the numbers that you think are meaningful to look at. And then you can report that in your study. Okay, so if you run this, first of all, you will see that the test of moderators, the p-value is 0.03, right? It tells us that this is significant. There is something here, right? As coverage increases, there is a change in whether media campaigns were effective or not, right? So you will then look at the prediction interval. Okay, if you look at the prediction interval, you will see that if the coverage was 10%, then we had 1.17 as the relative risk, and it was not significant. So which tells you that if the coverage has to be high enough up to some point before you begin to see effect. And if the coverage was 1.42, or if the coverage was 50 1.42. If the coverage was 90%, 1.73. There's an important caveat to note here, and that is that this is assuming that there is a linear relationship between the coverage and the results. But that is not always true in real life. Sometimes it might be that there is no relationship, and then when you get to some point, the relationship goes like that, you know. But you know, what we're really doing is just trying to approximate the truth in some way. Okay. So one other thing that we might then do is that we might want to re-examine the coverage as a dichotomous variable. We can create a dichotomous variable based on the coverage. Is it greater than 50% or based on greater than 60%? I will not go through that, but I think that I will stop here and we'll take a break. Just before the break, we went through inference analysis, cumulative meta-analysis, and heterogeneity. Basically, we explained that inference analysis is essentially, you know, we have an analysis that we've done, a pooled analysis, and we're trying to understand whether one specific study has an outsized influence, you know, on the pooled estimates that we're looking at. And for cumulative meta-analysis, we explained that what we're really trying to do is examining whether the time or the epoch has an influence on the results. And I gave the example of HIV as well as surgery, where the approach to treatment changed significantly, and that can have an influence on the pattern of the study findings that you get. Okay. And then we talked about heterogeneity, in which case we're trying to understand whether whether other study characteristics might have an influence on the results, and trying to understand how that is so, why. So the key thing to take away is that everything that we have learned in the last 1 hour or so, they are not absolutes. It's basically you think about this, you have a hypothesis about, or maybe coverage has an influence, maybe age has an influence. You know, based on that hypothesis that you have, conduct these analysis, and then depending on what you find, you will try that. Then you go back into your data and try to understand exactly why you are finding what you have. You know, so this is not a straitjacket where this is prescriptive or this is what you have to look at. This is a question of, as a scientist, you ask yourself, what do I expect to see? Why do I expect to see it? And then proceed to test it. You know, that's the way to think about this result. Okay. So now